But what this is all about is a way we use our hardware tool at Twister and integrate it with our thermal simulation. And I'm just going to walk through sort of what it is we're trying to overcome and how we can do it with these two sort of unique methods coupled together. So I'll give an introduction. You know, what are the thermal challenges that I'm talking about? What is it we're trying to do or trying to figure out? And then I'll get into the general principles of packaged thermal transient measurement. And realistically, to get into that completely, that's usually when I do seminars, it takes like 2 or 3 hours to get all that done. So I'll ask you guys to take a leap of faith and trust that what I say I can get out of it, I can get out of it, but I'm not going to tell you exactly all the steps that go into it. So that takes a couple hours longer. But the message that you get out of this is really important. That's the key take home. We'll go through the calibration process, how we bring the actual measurement and the simulation together in a calibration. And I'll just kind of go show you how that's really sped up in our tool. So I'll show you a manual way we do you could do calibration, and then how our tool works to do it. Okay, so I'll just go right along here. So what are the challenges? Obviously, you know, you see stuff like this all the time. We want improved accuracy. So a lot of times when you hear people talk about CFD, they say 5 to 10% is good. Well, we think we can do better. So, you know, if you have low temperature predictions, you're going to run into field problems. You might have over temperatures and run into things like that. And if you're too conservative and your temperatures are sort of over-designed, then your costs will go up. You'll over-design the product, and over-designing usually means more costs. So that's kind of just a simplification of what we're trying to eradicate with this process. This slide here, the biggest takeaway is that no one really knows all that well what their accuracy of their simulation is. So these pie charts are the people that think they're within 1% are very small. The rest are, you know, within 10%. Or this 27% of people that use CFD are saying they're 10%. With this, at the end of this, we think it will be better. So the idea is to improve everything along the line. You know, better design decisions, and this whole process is predicated on the product called the Twister. And where we can use it in the automotive industry, we've seen it used in these kind of places. So LED lightings, we can do measurements of the LED using Twister and simulation as well. We've got a nice suite for that. Steering control units, engine control units, braking control units, all those places where your components are on a PCB, there's a conduction path. That's an excellent place for use of this process that I'm going to go through today. Okay. And then, of course, converters and inverters for electric hybrid type vehicles. So the challenge is what is that challenge? It's to understand that thermal structure. What is the thermal structure? You know, we've got some metrics you've heard in the industry, junction to ambient, junction to case, things like that, but those are one point in space and sort of a temperature across, and they're really hard to define what the thermal characteristic is of a component or a component in a full system. So with this hardware, we're able to measure the resistances and capacitances in layers and do it accurately and consistently. So methods that might be used today that you'd see in the field are, you know, an X-ray, where maybe in time you might see some delaminations in the component. Well, you can see it, that's great, but you don't know what the thermal impact is. And since my specialty is thermal, we want to know what's the difference in resistance in that component, and we're going to run into thermal issues because of it. And that's where it's just qualitative, and it doesn't tell you what the thermal impact is. So to get into the general principles of thermal transient measurements, I have the next slide, some slides to do that. And you'll have to take somewhat of a leap of faith. Like I said, usually it takes 2 or 3 hours to go through the explanation, all the steps we do and how the hardware works and whatnot. But in the end, what we come up with is the structure function. So if I just take a minute to explain structure function. structure function is the thermal resistance, degrees C per watt, on the abscissa, and the thermal capacitance on the ordinate, the volume times the specific heat times the density. And what it is you work from the heated area, usually the die, and you generate this structure function there out. So you have die attach, some sort of a heat spreader in there, maybe an insulation or solder layer, and then more of a build-up as you go out. And then you get to the ambient where it's asymptotical, and the ambient is very straight up and down, and the ambient is considered to be an infinite source. So that's where you can handle a lot of capacitance. Yeah? But this is, in isolation, all not that much very interesting. It's when you use it in different ways to understand an analysis. And in a nutshell, the way we get this data is with the T3ster, and we wire up a device. We do that in a special way such that we can monitor the temperature at that die. We give it a power step, and then we look at the voltage over time on the die. We use a calibration characteristic curve to know what the temperature is over time. And that temperature over time we use to get that structure function. So I'm telling you in a nutshell how we get that. Okay. So the idea is that we take that measured thermal structure function, and when we go to our analysis and create a structure function as well, because we can get temperature over time in a thermal simulation, yeah? So the idea is you take a structure function you actually measured and a structure function you did in simulation and compare the two. So a lot of times you'll see a big difference in your structure function between an uncalibrated, what you measured and what you thought was a good model that you built. And the idea is that you want to calibrate that model, your simulation, to be just like your test, and then you'd be assured that your accuracy would be much better, both in simple resistance terms and in a transient sort of case. When you're changing power profiles, your temperatures should track in your simulations as they would in test. Okay? And then we would know that the object is modeled correctly. We'd be assured of the 3D temperature of the part and system. And then we'd know that the response of the system that we have in simulation would be accurate. Okay? So the way we would go through a calibration, and I'm already getting behind some, but the way we go through is the typical way might be you put some thermocouples on something, you change some resistances of things, and then you might get the right answer, but for the wrong reasons. It's not always immediately apparent. So adding this transient aspect to it is a huge benefit. So I'm going to run through a sort of the way we might do this. So the idea is we set up a test with our in a controlled environment, and then we also set up a simulation model. And we would go through the way we would go through this is we would derive the experimental structure function. We'd measure it, take the structure function. Then we would replicate the test setup in Flotherm. And we'd take the temperature over time and create the structure function. And then we'd compare the deviations in the structure functions and make adjustments to the simulation, and then kind of repeat that until we have the calibration done. Okay. So what you might see is a true structure function. This is from a measurement. And then what we might do is on the same graph apply what we got in the simulation. So if we look at this sort of zoom in area here, you can see the structure function's different. So I know just because I've used it before and it's an engineering tool, you'd get accustomed to this. But this first part is a die, and then you go to die attach. So we need to make some adjustments in this area in order to make them the match. And the idea with the structure function is you can see it's very different. What we like to do is start matching at the beginning and work our way out. So what do? We start at the nearest die and work our way out. So we want to kind of get this more in line with what we see here. This is the structure function, in a zoom in of it. This is the derivative of the structure function. So wherever there's minimas or maximas in the slopes, we'll see peaks over here. So it's just another tool to help aid in understanding structure function. So what we do, we don't take our simulation model and say, well, the conductivity of copper is doubled or double the specific heat. We make things more realistic in the range that it's possible. So what happened here is they weren't careful enough with the die and the way the die works. This was a test vehicle, so it had multiple dies. So what they did is just refine the die, actually put in the detail for the bumps under that die, and what you see, lo and behold, is what was before is improved to now overlap better with what was measured. So those details were important as far as what the structure function was seeing. Okay, and we'll work our way through. So the next is, you can see they're lining up at the beginning, but now there's some difference here. So this area isn't as, and because it's on the abscissa or flat, that's a resistance. The resistance isn't high enough. So we have to add resistance to this here and make changes, and we get more in line with what the actual measurement was. And we work our way through, so on and so forth, the TIM2, the grease into the environment, and so on. We make these changes, and we keep tweaking the simulation until we come up with an even match with the structure function. So now the structure functions overlap. So when my simulation models takes on a stimulate as the test would, we should get the same temperature results. Okay? So that's kind of working through it by hand. But in our software, in Flotherm V11, we actually automated this process. So in V11, we are able to bring in the T3ster data into the software. And for those of you that don't know, Flotherm is a computational fluid dynamics software that's specific to electronics. So it has all the tools in it to help you do electronics cooling. Okay? So it's very easy to bring in a PCB, bring in detailed components of ICs and MOSFETs and IGBTs. But then it allows us for direct comparison right in the tool. So what we do is walk through the steps here. Is first create the device. And we have packages that help you create a detailed component very quickly. So you build that up. You build it as close to the real representation as you can. And the system. So if it goes on to the system as well, the PCB it's on, you would add that in as well. Depends on what you're looking to calibrate. And this example is just talking about the component itself. The next step is you nominate the parameters that are allowed to vary in the calibration. So a lot of times, like you know the bulk conductivity of, say, die attach, but when it's actually applied, there's some resistances that can occur and different things that can occur, as well as the thickness that can vary a little bit after the solder flows and whatnot. So you put a variation in there for things that you might not quite know. The size of the heated area on the die, that can have a big influence. You know, die attach bulk resistance and different contact resistance. Anything that you're not sure of, you can put a variation in there. Okay, you go do the T3ster measurement and export the data. And then you bring that into the Flotherm environment, and that's where you've set up the parameters that you're allowing to vary. You select the temperature-sensitive parameter. I didn't get into the temperature-sensitive parameter too much, but that's what was actually physically measured in your test. You tell it exactly where to isolate that. And then from there, you're ready to go to the next step. And the next step is where you tell it to create a whole bunch of different models based on all those variations. So you can do a design of experiments for how much time you have to run all these different simulations. Okay? So you go ahead and run those simulations. And you'll have a whole array of simulations with a bunch of different varied parameters in there. And what happens is you'll get these, for each of the cases, you'll get these structure functions compared to the original structure function. And it'll give you the lowest cost functions based on the difference in the structure functions, how different they are. And you want the lowest cost function. And once you've determined that, the one that has the best fit, I should show you the bad fit first. So here you can see, the original structure function of the simulation is very bad compared to the test. And once you're done and you've selected the lowest cost function, the structure functions line up right on top of each other. And at that point, you can take that model, do a save as, and then that's your working model, and you've got a calibrated model that should perform as the test did. And then you can run it in different environments. So a quick example of that is we can look at this part here. This is the uncalibrated versus the calibrated. And you can see the temperatures could wildly vary with a step input. And the peak temperatures, average temperatures, and temperatures throughout the body will be very different. And here's an animation where you can see this top one is the calibrated. So you can see there's a higher sort of gradient through here, where the one that was the original best guess has a different temperature profile, which can be, if you're sending results off to someone that's going to do stress analysis with that data, it could be very, very different results. Okay, so I'm winding down here. I think I'm doing good on time. Yeah. For summary, calibrating is the best way to make sure that the critically important parts, your junction and your components, are going to be very accurate in your simulation. And that'll maximize your model accuracy. So you can, when you're running this simulation in different sort of environments and however many tests you want to do later on this, you'll be sure that you're getting very accurate results without a lot of swag in the results. The other thought is that if vendors if you start using Flotherm and vendors send you data that they say has been T3ster certified and they've measured it, you can rest assured that that simulation model that you're going to get is a very accurate model. So the idea we'd like to see someday is, the original vendors of the components doing some of this work, and a lot of them have this tool. So we'd like to see it in the supply chain as a sort of a standard, if you will. So, this is actually this synergy between our test and simulation. I don't know that any of our competitors or anyone else in the market does it. I mean, there may be some homegrown things like this, but the way we do it from the junction out using simulation and test is, I think this is the only place that it's commercially available. And then, of course, in the version 11.1, we've automated. So you could do it by hand, but we've automated that process so you can quickly and easily get you that simulation very, very accurate. And then the risks associated with good enough, a little over-designed or a little under-designed, kind of go away or have a reduced chance of happening. And you don't have to rationalize, well, it's good enough, it's accurate now.